afraid that the presenter's going to bite you.
Yep, exactly.
You probably will.
I know you will. Almost showtime. Yes, he is. He's hat on this. Tony?
Yeah.
He's all wired up and ready to go. Just counting minutes.
You want to get going?
Take your mask off when you speak.
All right.
See you. Good morning, everyone. Welcome to the Nearfest Forums program. I'm the Forums Chairman, and starting off our program for today, Friday, we're very pleased to have Tony Fisher, who's going to talk about troubleshooting stuff, which is always a very important thing because stuff always works. Tony, take it away.
How do we make this projector work? So I'm gonna preface my talk with a political statement, and this is not a paid political statement. I have not been asked to do this by anybody, and I'm talking about the election for New England director.
Can you turn your mic?
All right. Okay. Can you hear me now? Hello, test. 1, 2, 3, 4, 5.
Yeah. Thank you, Ben.
Okay. So there are 3 candidates running, and it's 2 Freds and a Tom, and they're all personal friends of mine, and so it's very difficult for me to come out and say that I endorse one candidate over the other 2 because I'm obviously, you know, alienating a couple of guys. But I think I can communicate my thoughts without specifically endorsing anybody. I think a lot of the candidates talk a lot about having a presence in Washington or doing something for people who have homeowner agreements or spectrum defense. And I think all of that is a moot point if there aren't any hands around to support that effort. So
Tony, probably should not go in this direction.
All right.
Should save this one.
Okay. So I'll go on to my regular presentation here. Anyways, I still don't see anything on the screen. I think we have to do something on this computer to make it come up.
Should be.
I can't even see the keyboard here.
Signal should be going.
I can't figure this out. Probably something has to happen here, but I can't even see the keyboard.
We're already troubleshooting.
There you go. Well, I got a picture here, and I don't have a picture there.
So you're actually on the Zoom page on the PDF page.
Did you like something?
So that was what you were looking at was the actual Zoom. So,
All right. Looks like it's coming up.
yeah, it's there. It's trying to push in. So make sure you get that. Okay. So, yeah, we have some problem with the projector, I guess. It's showing on the screen okay, but it's not good straight across.
try hitting F5 or F8 or?
Well, it's coming this week.
Please check your sound. We're not getting outgoing sound.
Yeah, usually have to send it from the local stream to the VGA. Usually goes up to the.
Yeah, it's already going over. It's already, because this is from HDMI two, it's just getting split along the areas. So it's projected sound issue.
It worked before though. Yeah, it did.
But what we can do right now,
More people coming in, so we'll fill the room up by the time we get this working.
Probably people who made the trip to the Arts and Crafts building, and that's not bad.
Yeah, that's what, we have a lot of time for that.
try this to see if
Exercise.
see if we'll try the projector.
What's that? Yes, it's at my camper. I'm across from the bars now. So follow me back after this and I'll get it.
Camper.
Across from the bars guy. So Rick, I radio.
Oh, okay. Okay.
All right, that looks good.
So we'll skip the.
Okay, anyway, my talk is about troubleshooting stuff, and I didn't say troubleshooting electronics because the same principles can be applied to anything else. Here's the agenda. It doesn't work. Did it ever work? What went wrong? Visual inspection. Why troubleshoot? Diagnosis. Stimulus response. What am I expecting?
Looks like we're going to be out of luck.
Can't read anything.
White on light.
White on light blue.
Well, it wasn't white. It's clearly visible on this computer.
The best we could get, unfortunately.
All right, I'll just keep going. And so anyway, observation tools, circuit flow, segment halving, parallel flow, Sherlock Holmes, Hunt's law, intermittence, safety, the usual suspects, and then I've got some interesting war stories at the end, and if we have time, I'll take some questions. So basically, your whiz-bang doesn't work. An electronic device doesn't function as expected. Old reliable is now not so much. Or maybe a new design doesn't work as you hope. Maybe it's something you built from a magazine article or something you designed yourself. So you have some expectations for it, but it's not like you can say, well, it's broken, it's under warranty, I'll send it back to the manufacturer. So what do you do now? And we'll talk about the diagnostic process, which ultimately we hope leads to repair and gets you back going again. It's important to start with zero assumptions. You can't start out thinking that you already know what's wrong, because you're probably incorrect. And like they do on the CSI show, you follow the evidence, follow where the evidence takes you. So the device was functioning normally, and then it stopped working. Something changed. How do you figure out what changed in order to fix it? Well, a really good method for figuring out how to fix something, or figuring out what changed, is a method called Kepner-Trigo. And this was taught back to me in the early 80s at Hewlett-Packard. And if you can get your hands on a book called The Rational Manager, it's a funny sounding book and it sounds like it's about management, but it actually has a very good description of a process you can go through to figure out what changed. And a lot of times it's not what you think. It's something really off the wall. Or you can go to the in case of difficulty section if you have a heat kit. Heat kit actually spent as much money writing manuals as they did building kits. And so their in case of difficulty was really great. You're going to use the diagnostic process to figure out what changed in your electronic whiz-bang box and hopefully undo the change. In other words, replace a burned out part You're going to try to locate the bad actor, replace, and then verify that that has fixed what you're looking for. And rinse and repeat. Sometimes there's more than one part that needs to be replaced. We'll talk about that. And you also have to be aware of collateral damage. So sometimes one part will fail, and that'll take out a whole bunch of other parts. An important question to ask is, did it ever work? And this applies to the situation where maybe it's something that's your own design, or you're building it from a magazine article, and it's not like you've ever had this thing working. Essentially, it doesn't do what you expect, but you've never had it working, so you're not really sure what to expect. Maybe it's your expectations that are wrong. And this requires a slightly different approach to troubleshooting and diagnosis. You can't compare it to a working unit because this is the first one you've ever built. So if you had two radios on the bench, one working and one not working, you could compare voltage measurements in one or the other and see, if I use that to help you figure out what's wrong. But if this is the one-off, the first time you've ever built the thing, you can't do that. You have to have valid expectations of performance. And you get that by comparing what's actually happening to your expectations. And your expectations can be based off of, if it's your own design, what did you design it to do? It can be based off of theory. So if a resonant frequency is off, you can use the resonant frequency formula to compute what you expect. Or you can, maybe if you're using simulations like LT-Spice, a program that you can put in the circuit and it'll tell you what the circuit's supposed to do. You can compare LT-Spice to what it actually does on the bench. Or if it's something you're building from a magazine article, your first alternative is to see if there's any explanation in the article about what it's supposed to do, or what's going on if it doesn't do what it's supposed to do. And then the second alternative is you can email the guy who wrote the article and say, hey, what the hell? Why doesn't it do what you said it was supposed to do? So the first thing to do is a visual inspection. And so you're looking for visible evidence. If this is a device that was working and stopped working, on the occasion when it stopped working, you may have heard some funny noises, like breakfast cereal. Or you may have observed some smoke signals that may have been telling you that something was incinerating itself internally. I got a great story. At one time I was debugging a computer that was built into a monitor, and I had the cover off, and I was going all around trying to figure out why there was nothing showing up on the monitor, and my wife walks over and says, oh, that thing looks like it's all burned out. Made me feel like pretty stupid. Here I am, doing the high-tech technique, and she just found it right away because it was obviously burned up. So look for crispy critters in there. Follow your nose. If you don't see the crispy critter, but you had some smoke signals, oftentimes you can sniff your way around, literally. Look for overheated wires, PC board traces that are overheated. Those can be clues that can lead you into the section of circuitry that's not working. Look for capacitors that don't look right. I had a Samlite's power supply, and all of a sudden it put out 0 volts and blew its fuse. And I opened it up, and it has some filter capacitors on the output, and one of them was obviously swollen, and it was gone bad. You can look for cratered ICs. So if you look at the top of integrated circuits, they should have a nice smooth surface. Sometimes you'll see that there's just a little bit of a bubble. Other times it'll actually blow a big piece out, in which case that's accompanied with some acoustic effects. But all of these can be visual hints in terms of where to look in the circuit for what's going on. So, assuming that you don't get lucky and have your wife show you where the burned out resistor is, then you start the diagnosis process. And troubleshooting is a process to find defective parts, or maybe to find a defective design. So there are a number of things you can do. There's shotgunning, where basically maybe you replace a whole board. Maybe you could buy a board from somebody on eBay and put a whole board in, or you could replace a whole bunch of parts. Or you can take a targeted approach where you actually narrow it down and you find the one component that's gone bad and you replace that one. Definitely in the diagnosis process, you want to take advantage of the way the circuit works. You want to look at how signals flow through the circuit and use that as part of your diagnosis technique. And we'll talk about some specific techniques to find the point of failure. So the question is, why troubleshoot? Well, the answer is, it's cheaper to fix something than it is to replace it. Obviously, this radio doesn't work, I'll throw it away, I'll buy a new radio, I'm in business again. Well, that's the checkbook engineering approach. But a better method is to try to find out if you can find a particular part and replace that part, and then you're back on the road again without spending a lot of money. And as I said, you can shotgun it, where you just replace a whole bunch of parts. You know, well, it's something wrong in the balance mixer, so I'll just replace all the caps. And a lot of people work on boat anchors that way. So a typical part that fails in boat anchors or over equipment is capacitors. And so a lot of times they just go through and wholesale replace all that capacitors. And within reason, I don't necessarily personally agree with that approach, but you know, that has its place. And then there's the targeted approach. You find the smoking gun or the particular part that's bad and you replace it. So we'll talk about stimulus and response. Basically, this is fancy language for the fact that something goes in and nothing came out. You connected the antenna and there's nothing coming out of the speaker. Or you push the button and nothing happened. The question is, where did you lose the signal? The signal went in, it didn't come out, it got lost somewhere. So you use circuit flow to narrow down the location of failed components. And you have to control the stimulus, so you have to have something coming in. If you connect an antenna and the bands are dead, or you know, the coax is cut, that's not going to work. So you have to have a known good input. You have to have something that you know is going to make the circuit behave in an expected way. And then you have to have a way of knowing that the output is working. So the known good input is the stimulus, the expected output is the response. So what are you expecting? Once you dive into the diagnosis, you need to be looking at internal nodes. And by looking, I mean various ways of figuring out if the internal voltages or currents in the circuit are doing what they're supposed to do. You need to know what measurements you can use to distinguish a working part or a working circuit from a broken part or one that's not working. And we use many different tools to examine electrical parameters of the circuit. So for things that worked before, you can compare your readings, your measurements in the circuit to the manufacturer's info. So for example, going back to the Heathkit guys again, the Heathkit schematics are always annotated with DC and AC and RF voltages. So you can go through and look at a schematic and take voltage measurements and pretty quickly know that you've got everything's right here, and then all of a sudden here it goes bad. You can compare it to a known good unit. If you happen to have two of these boxes, you can check one and then look on the one that's working, okay, that's 5 volts, and the one that's not working, that's 0 volts. Well, that explains the difference. That's a change. Or another technique is if you took some measurements before it broke, then you can figure out that gives you a clue after it broke. And that's really applicable to your antenna systems. So it's really good if you install the new antenna and you've got it working and it's great. Right away, you should make some SWR curves on it, or do some TDR pictures on it. I did a talk on TDR, which is time domain reflectometry. And that's a way of looking at where there might be a problem in your coax. And so whenever I put in a new antenna, I do a bunch of SWR curves and I save them on my computer. I do a TDR thing and I take a picture of that and save that on the computer. And so that later on, when the squirrel chews my coax, I can go back and compare and see what's going on. So for things that never worked before, like something you designed yourself or a project from a magazine, In that case, you have to go to the designer's info, and if you're the designer, then you're on the hook for it. You have to go to theoretical expectations, or you can go to simulation. So, we're going to talk about controllability and observability, and that's the same thing as stimulus and response. Controllability means injecting a test signal to force some internal node in the circuit to behave in a specific, predictable, observable way. You're going to put something in and you'll see the ABC line is going to go up because it's a strong RF signal. And the kind of stimulus tools that you use to inject signals to make this happen can include a bench power supply, an antenna, a microphone, or any other standard input, a signal generator. It might be an audio generator or an RF generator, a pulse generator. You can use a station transmitter, although you have to be careful with that because that might apply a lot more power than you want, and you could potentially damage something or damage your transmitter. Then the next thing is you want to take advantage of circuit flow. You want to look at the schematic and figure out how signals are flowing through the circuit. And circuits almost always have a directional flow to them. I've found almost always they go left to right. You look at a schematic diagram and something goes in here on the left and comes out over here on the right. Left and right for me, opposite for you. So if you follow the path of the circuit, this helps us to find the problem. The circuit flow is usually linear. It usually goes through one thing and the next thing and the next thing and the next thing. There are some exceptions to a straight linear flow. You can have parallel paths where it goes through multiple paths at once. You can have feedback loops where a signal comes back to an earlier point in the circuit. And schematics generally represent circuit flow from left to right. And once we know that there's a path through the circuit, then we can use what's called segment handling. So at the top level, here's your box, antenna goes in, nothing comes out the speaker, the fault's in the box. Now, if we cut the box in half, which we can do virtually by taking the cover off and using a scope probe at a node in the middle of the circuit, we can see if the signal made it to that point. And once we've done that, we've eliminated half of the circuitry. Either it's good, in which case the input side is all fine, you don't have to look at that again, or it's bad, in which case that's where the problem is, and you don't have to worry about the rest of it. Now, there are a couple of caveats. So one of them is that we're kind of assuming a single failure, so we have to watch out for what I call Hunt's law. And if we were successful, we'd cut the possible locations where the fault could be in half. And basically, we just rinse, repeat, we do this over and over again, narrowing it down to a smaller and smaller piece until hopefully we get down to one component that's bad. So, I think you can actually almost see this picture. This is a block diagram of a Heathkit HW101. And so here's your microphone. This top path is going left to right. And this is the transmit side of a transceiver. The bottom path is actually going right to left, and this is the receiver part. But in an example, we put a signal in where the microphone goes in, and we use our scope to look at the signals right here in the middle. And we can see that the signals are good, but there's nothing coming out over here. So that means that we've isolated the fault to this half of the box. And we can just keep doing that. We can cut it down to here. We find out, well, it's still bad. And we cut it down to here. And we say, well, that's good. Now we'll go to this piece. And we'll say, okay, it's good to here. That says it's got to be in this block. And that's how you can use segment handling to narrow down the region where you're trying to find the beds that are bad. So I talked about some of the exceptions to this nice, simple linear flow. One of them is a parallel path. So sometimes you have multiple signals that come together in a circuit and get combined. And sometimes you have a signal that starts out and actually gets split and it goes in two different directions. So that's something that can confuse you if you're trying to do segment handling, and it's important to understand where those occur. And then the other one is feedback. So here's a picture of a common op-amp circuit, and basically what's happening here is a signal from the rest of the box is coming in here, and it's getting amplified by this operational amplifier, and it's coming out there. But part of what controls the gain of this amplifier is this feedback back here. And if this is wrong, it could be because something on this is wrong or something on this path is wrong, and you have to figure out which. And then here's a couple of examples of parallel flow. Again, this is the speech amplifier input on an HW101. You have the microphone input, and then the audio is going off to the right to go into the transmitter, but they also pick off some audio and it goes to the box amplifier to trip the box. So in this case, if the radio transmitted when you put it into transmit manually, but it wouldn't go in the box, then you'd want to be following the path that took you into the box amplifier. Or vice versa, you'd want to be following the other path. And then also from the HW101, here's a case where there's two inputs going into a circuit and one output. So this is a balanced modulator, and what's going in on the left is the audio, what's coming up from the bottom is the RF from the carrier oscillator, and what's going out is the modulated audio. So again, you have to make sure if you're not getting what you expect out of this, it could be either one of the two input paths, and you have to figure out which it is. So an important thing to remember is Sherlock Holmes, which is when you've eliminated the impossible, whatever remains, however improbable, must be the truth. And this has bit me in the butt so many times, I just can't count. Another one is Hunt's Law. And Hunt's Law goes like this. Everything I've told you up until now has been assuming that there's one failure. Hunt's Law says, well, a lot of times there's two failures. And not only is there two failures, but one of them hides the other one. Okay? So your ideas about having a single point of failure go out the window. So bottom line is, when you start off, go ahead and assume single point of failure, but be open to the possibility that Hunt's Law may be there. And this is named for Barry Hunt, who was an engineer colleague of mine at Hewlett Medical. Larry knows about Barry. Anyway, he kind of started this up, and it became Hunt's Law. Intermittents. Intermittents are the hardest type of failure to diagnose. And that's because you have to make it fail. If it decides to work again while you're trying to debug it, you're not going to learn anything. You've got to get it to fail in order to figure out where it's failing. So there are a number of things that we can do to deal with intermittence. One of them is a storage type oscilloscope. A storage oscilloscope is one where when the scope triggers, it saves the picture for you. And so if you had a radio that worked most of the time, but every once in a while it would stop transmitting, and you had a signal in the radio that you knew was going to go high when it's supposed to transmit, you could set up a digital storage scope to trigger on that signal. And then the one time that it stopped transmitting, you would have saved a picture of what was going on when it failed. And storage oscilloscopes used to be wicked expensive, and nowadays they're very cheap. You can buy a really great digital scope, which automatically has the storage capability in it, for like a couple $100. I have a Handtech scope. It's really small, light, portable, color TFT, dual channel, 70 megahertz. It's great. You can use the Fonzie technique where you go up in your belly and you see if that has anything to do with it. That'll give you a pretty good clue as to if it's a mechanical issue. You can correlate the failures with environmental changes. Does it change the time? How long has it been turned on? Does it have anything to do with the temperature of the box? Does it have anything to do with humidity? You can use different techniques like freeze spray or soldering iron to intentionally heat or cool specific parts of the circuit to see if you can make the failures come and go. And with intermittents, it just takes patience. It can take a long time, but it's still the same process. You got to get it to fail, and then you have to apply your diagnostic techniques. And then I'll also say something about safety. Essentially, in order to apply these diagnostic techniques, you have to open up the box and look at internal nodes. And that can create safety hazards, both for you and for what's going on in the box. So for anything that has high voltage or high current in it, you always want to follow safety protocols, including but not limited to removing the power, de-energizing and discharging the circuit before you make connections to the internal nodes, before you go mucking around in there. If you have to do something in there with the power on, keep one hand in your pocket so your body can't create a circuit across the high voltage. Remove all your metallic jewelry, take off your rings or watches or whatever when you're working around something that could provide a lot of current. And the physician's oath, first do no harm. You want to take precautions to avoid making matters worse. I've done it myself dozens of times. You're in there mucking around and you accidentally, the ground with the scope probe hits something and you lose the power supply. Now you get two things to fix, and Huntsville is immediately in play. So now we'll talk about the usual suspects. Some parts of electronic circuits fail more often than others. And I've tried to put this kind of in the order that they fail at. And this is just based off of my own personal opinion. There have been a lot of reliability studies done that could put numbers on this and give you a more accurate explanation. But basically, I think number one on the list is connectors. Connectors are basically two pieces of metal touching each other. You can get oxidation, you can get corrosion, they can lose their spring tension. There can be all kinds of mechanical problems that will cause that connection not to be the good solid connection that it needs to be for the circuit to work. Cables are also bad, flexing, shorts and opens. I'll give you an example on this one. Ice maker quit in my fridge. The fridge is about 18 months old. And this is not the first time I have decided to fix my own refrigerator. And so based on the usual diagnostic process, you start fooling around with the ice maker and you see if it's cold and you see if there's water coming in and you see all this crap. And I was getting nowhere. So YouTube to the rescue. And this is a really important diagnostic technique that I don't think I mentioned in the slide. But Google everything, because you'll be amazed about the fact that somebody else has had your problem and they solved it. I Googled the ice maker doesn't work in my Whirlpool refrigerator. And it comes up with this thing that says, well, down at the bottom of the door, there's a cable that goes into the door, all these wires. And you open the door 100,000 times, getting your eggs or whatever, and this big wire's breaking. It's just a simple bending until the wire breaks. Well, that was my problem with the ice maker. Of course, by then I'd taken the ice maker apart to see what was inside it, and I couldn't get it back together again right. So I had to buy a new ice maker anyway, but that's beside the point. So cables are an issue. Anything that operates at high voltage, high temperature, high current, and those are relative terms, but I'd say high voltage is over 50 volts. High temperature is probably anything over 70 degrees C. High current is anything over 3 or 4 amps. Those are circumstances where if the circuit goes bad, you can get thermal damage right away. You can cook the IC or melt the solder. I've had situations where the device was drawing so much current that the solder melted and the parts fell off. Overstress or misapplication. So this is really a design problem. And so if the engineer put a quarter watt resistor in and it's dissipating 3/8 of a watt, it's going to overheat. Eventually it's going to fail. It might not fail right away. So this happens. I would have to say that the cables in the refrigerator are overstressed in this application because they aren't properly strained. Any external connection can be damaged by something that happens outside the box. So static electricity can damage external connections. Lightning is an external connection. So those are opportunities where failure can occur. And then some parts have finite lifetime, like electrolytic capacitors, old paper capacitors, black beauties, oil field capacitors, silver microcapacitors. A lot of those parts, the engineers design a part, they build a part, they test the part, maybe they test it at high temperature for a year, but you're expecting it to work after 50 years. Okay, all of our stuff is old. We all have old stuff. So now I'll talk about a few war stories, and we'll see how far we get on this. An AL1200 amplifier that had no output on any band. Same amplifier, different time, had crazy loading on the low bands, and it was arcing. There are a couple of examples where I've diagnosed problems in commercial radios that were design issues. So the 756 Pro from ICOM had a problem with audio thumping. It also had kind of crappy sounding CW. I had a case on rotor cable, and that was an example of the Sherlock Holmes principle. And so I'll go through some of these. This is the AL1200. So the symptoms are that I went to load it up and I was getting absolutely no output on the main band. And fortunately, my procedure for loading up amplifiers is I always start at very low drive. So I was starting with a drive that was low enough that all it should have put out was about 200 watts, which was fortunate because if I had used all of my known good settings for 1500 watts and blasted it, I probably would have blown something else up. So I had no output on any band. High voltage was good. Grid current in idle was good. Grid current, when I drove it, seemed to be a little high, but again, I was driving it really lightly, so it was hard to tell. Anyway, opened it up, and it turns out that there is a dead short of the coax. So this piece of coax comes from the tank compartment. So this is basically the output of the amplifier. And then it goes up along the center wall to the transmit receive relay here. And right here where it comes around the corner, in my amplifier, it had a very sharp bend. And it was also foam coax. It wasn't solid dielectric coax. And so what had happened is that bend, after a reading contest or something, it got hot enough so that the center conductor migrated and touched the shield. And it was essentially a dead short to the output. And I replaced that piece of coax with a nice piece of RG142, and I'm off and running. So this is a case exacerbated by high voltage, high current, high heat. And it's definitely a misapplication because they shouldn't have bent that piece of coax so tightly. There's a guideline for bend radius on coax. And they also shouldn't have used foam coax, so that was a misapplication of foam coax. So another one, same amplifier, in the middle of the contest, I go to operate 40 meters, and the loading isn't where it's supposed to be. I keep little pieces of paper in front of the amplifier with pencil marks to show where all the settings should be, so I can get to them quickly when I change bands. And I went to 40 meters, and it wasn't loading up, and I found the loading control was all the way over to the left. And so anyway, on debugging, I figured out that it worked fine on the high bands. 20 meters and up, it was perfect. 40 meters and down, it was really wacky. The ultimate determination turned out to be these contact fingers in the band switch. So this part of the band switch is rotating on the shaft, and it has a couple of contact fingers that come out and make contact with buttons on the fixed wafer. And again, the heat had caused these pieces of spring metal to lose their tension. And so the fingers weren't making good contact with the buttons. And the choice here was to replace the band switch, and that's just a horrible job. And so the alternative was to just go in there with a pair of gloves and very carefully give them a little tweak. And so far, so good. And again, this is a high current, high heat situation, and the spring metal is fatigued due to a lot of heat. I'm not really sure I'd call it a misapplication because I am a contester and I do drive the amplifiers pretty hard. Well, I'm going to go back to the previous slide to cover some of these other war stories. So when the 756 Pro first came out, everybody loved it. It was a great new radio. It had color TFT display. It was the first major radio DSP filters that you could adjust. Some people noticed that when they were listening to it with headphones, they could hear kind of a weird thumping noise, which didn't seem to really correlate with anything, and they didn't know what it was and didn't like it. And so Jim Jarvis, M2EA, and I worked on this and did a bunch of experimenting and also kind of took a lucky guess. And we found out that it was a design error on the part of Lockholmes. And they basically had two circuits that were powered by an 8-volt rail. And there's a nice bypass capacitor on the 8-volt rail. But that bypass capacitor was too small, which meant as this circuit drew a lot of current, it was actually moving the rail, which is making the sound come out on this one. So one circuit was like an IF thing, and the other circuit was an audio amplifier, and that's where the thumping was from. And the clue was that the audio thumping really sounded like an AM demodulated version of sideband. And that's pretty much what it was. So over here, we're listening to the whole band, the whole IF, and it's basically whatever the total level of all the signals is modulating the audio amplifier. And so we wrote a thing for instant kinks that appeared in the June 2002 QST. And of course, in the July 2002 QST, ICOM came out and said, well, you'll never hear it, and don't go in there and fuss around with the radio because you'll break it. So, and then the other one was Flutie audio on CW in this same original 756 Pro. And the best I can say is when you hear a CW note, if you're a CW operator, you really want to hear a pure tone. Just a nice, like somebody hit a key on a piano. Just a pure single frequency tone. And I noticed that the audio in the 756 Pro on CW sounded, at times, it sounded a lot like a train whistle. You know, kind of this funny, fluty sound. And I did a lot of digging, and I looked at the audio output of the 756 Pro, and I actually used a computer sound card and a spectrum analyzer piece of software. And so you can get software that will make your sound card into an audio spectrum analyzer. It's really good. You know, it's got lots of dynamic range. And I could see that when this thing was sounding fluty, that third and fifth order harmonics were coming up or appearing in the sideband. So if you like your CW pitch 400 hertz, you'd get something at 1200 and something at 2000 hertz. And that just made it sound like a train whistle, or made it sound awful. And I looked at the circuit on the 756 Pro and was able to figure out that even though most of the radio was designed really well and had this awesome DSP unit in it, after the DSP, from there to the speaker, they had the cheapest, crappiest little audio amplifier chip, and that was the problem. And the reason you only heard it on CW is because they had a nice low-pass filter for AM, but the low-pass filter is high enough that it was letting those harmonics get through. So another story is my rotator cable. I had an alpha spin rotator on my tower, and when I bought it with the controller box that go with the alpha cells. And that controller box works, but it's kind of crappy. And I wanted the computer control this antenna, and so I replaced the alpha controller with a green heron RT21. Green heron is like a Cadillac of rotator controllers. It will control any rotator, it will do things that they never thought of doing, like ramping up the speed and ramping down the speed. It talks to the computer, it's fantastic rotator control box. So I swapped the box out, set it all up for this way, and it seemed to be working. But then I noticed that I'd leave the antenna in one position and I'd come back and the box, the display on the box would say it was pointing in a different direction. Well, the way that this all works is that there's a Hall effect or a reed switch in the rotator with a magnet. And when the rotator rotates, the magnet goes by the reed switch and opens and closes the circuit. They have a 1K resistor there, so that if you accidentally connect a motor drive to that, it doesn't burn up the reed switch. And so I got this brand new box and it's not working, so the first thing I do is I talk to Jeff at Green Heron, who's fantastic factory support. You email him on Sunday night, I'll get right back to you before Monday night. And so I said, geez, you know, it doesn't seem to be working. And he says, well, measure the resistance of the rotator wires and everything. And I did that, and it was like about 1,100 ohms, which seemed about right for the 1K resistor out there, and the wires and all that. Anyway, make a long story, not quite so long, just went around a lot of stuff. I put my digital storage scope on there, and I could see the pulses going up and down, and that all looked fine. And Jeff at Green Heron says, well, you know, you probably have a bad connection in the rotator wire. And I had measured it with the ohmmeter, and it said 1K, but I did not realize was that it was intermittent. And I finally got it to fail. And then I went out and I looked at the cable that came in. And my cable comes down my tower, and it goes into a conduit that's buried. And at one time, the cable had been chewed up by some rodents. And so I had put it back together, put my soldering iron out there, soldered it all up, taped it up. Well, I went out and pulled that splice out, and it fell apart in my hand. And so this is a Sherlock Holmes case. Even though it was just impossible to my mind that the cable could be bad, it was bad. And we'll talk about a few other ones. I had a Raspberry Pi, and this is kind of a software thing. And I was trying to use the I2C interface on it, which is a way that little computers can talk to different devices on a very simple bus. And I found out that it was doing two different things at once that I was not expecting. First of all, it was doing some clock stretching on the interface, but also it was doing kind of an automatic speed shifting. So processors can run at different speeds. You know, with Raspberry Pi can run at different speeds. And what I didn't realize is that this one was set up to automatically throttle speed depending on the load. And so this speed shifting and trying to figure out the clock stretching was a case of Hunt's law. So there was definitely two things going on, and it took me a while to sort the two of them out. Back to the good old AL1200 in the middle of a contest one night, operating on 80 meters, and I would transmit, and I would listen, and when I went to listen, receive signals would like way down. And then if I just bumped the mic, you know, made it go in the box and transmit it, they'd come back up again. And then I'd talk to somebody, and then they'd go back down. Well, anybody who is contested knows that when that happens, there's one pretty good explanation, which is a TR relay and the amplifier is dirty. And So I ripped all the covers off. Of course, it's about 1,800 screws in the cover of the L1200. You know, in the middle of the contest, taking it apart, and that didn't fix it. And I put the cover back on. I think it's okay. No, it's broken. Take the cover off. Play with it, relay some more. You know, get out the typing paper and the deox and try to clean it up. Finally, I realized it only happened on 80 meters. It didn't happen on the other meters. You know, I slowed down enough to do a better diagnosis, which is to look at all of the facts. And this is what that Kettner-Trigo Rational Manager book helps you to do, is not ignore certain facts that would help you get to the bottom of it. And the bottom line is that it turned out to be a bad UHF union in the cable to the 80-meter antenna. Went outside in the snow, replaced the union, and I'm off and running again on 80 meters. I had a dishwasher. I'd like to fix my own appliances. When the dishwasher was new, we weren't really impressed with how clean it got the dishes. And then we were just really kind of disappointed with it. And then it started getting really weird. It wouldn't run, the lights would all blink and everything. Okay, so long diagnostic scenario, why isn't it working? Come to find out, modern dishwashers had a little optical sensor which looks for food particles in the water. And so if it has a smart cleaning cycle, it'll keep grinding the dishes in there until the food particles go away. And so it has a sensor, which of course is cabled up to a wiring harness that goes through the whole dishwasher, up into the door and everything else. And so what had happened is, first of all, the sensor had cracked. And so it was letting water, a little bit of water come in. So that's basically probably when we said it's not cleaning the dishes, because the sensor was bad. But then all of this water dripping down on the cable, on the connector, just corroded the hell out of it. And so now that's when it really failed, is when that cable went to hell. And on that one, my choice was, I could buy a cable, which was $90, but that's still cheaper than a whole dishwasher. And then, as I said, the cable is like everywhere. It goes to the motor, to the door, and all the lights in it, and the soap dispenser. And it's like, okay, here's the connector I need. Here's this rat's nest of wires that get soaping. I just cut the one I need off, splice it on, go off and run again. And then I think the one I'll leave for the last year is I bought a heat-kit AR3. And the reason I bought this is a heat-kit shortwave receiver. It's got 4 bands, A, B, C, and D. And the reason I bought it is because my earliest memory is looking over the shoulder of my father and brother as they tried to put one of these together and make it work. So it's part of my, my radio infancy. So I bought one for sentimental reasons, probably off of eBay. And I got it, and it kind of worked, and I was going through it, cleaning it up, and replacing anything that needed to be replaced and making it work. And it just didn't work on band B, which was the highest frequency. Just dead as a doornail, nothing. So I'm going inside and looking around, trying to figure out what's different about band B. That's the clue. It's only on band B. Everything else works. Most of the radios work. And it has a little section where it has 4 different coils for each of the bands. And on the band B coil, there's a splash of solder that's shorting the coil around. So that's why it's not working. But guess what? That solder was put there by the guy who built that kit the very first time, which means band B never worked. Somebody else never figured it out. And it was only, I just got lucky because I happened to notice this little splash of solder. So that's the end of my talk. We could turn the lights on. I'll take questions. Anybody who's got something that's broke, I'll take a guess at how to fix it, or whatever.
I was just going through my head as you were talking there. The contact, any of the contact intermittencies, especially on the older stuff. The Collins Collectors Association has a great section in there about the isopropyl, the pure isopropyl alcohol, and
So probably what they recommend is a product called Deoxit.
yeah, I was going to get to the deoxy, but and never to use anything too thick or
Yeah.
file a band switch or anything like that.
Right.
I have an S line that was made in '78, and I got it shortly after that used. I looked out, got it on the yellow sheets, or the yellow sheet, and guy in the state of Washington packed it up, sent it to me. Everything was like round emblem, beautiful, old date code 78. And it sat there for a while. I started using other things. I was traveling a lot for jobs. And I have a radio room, and even though it's somewhat sealed, the kitchen rafters is open. I have like insulation up there, but the oil burner guy did some service, and this wasn't my best technician that comes to the house. He caused a puff, and that black stuff got through the entire basement. My first thought was, what is this going to do to the contacts everywhere? About a year later, I fired things up again. And sure enough, I had that situation, certain bands on the transmitter and receiver didn't work. You can't see it. You can't see that oxidation. You can't see between the beryllium, copper, bonds. But I use the methods in the Collins Collector Association do's and don'ts, paying particular attention to the never do section.
Yeah.
Because in the earlier days I had used the Q-tips and files and erasers, after cleaning it up, didn't even get to the grounds. You should clean up, lift up all the ground lugs, what made them look good. They have a little oxidation in there, clean them up. Everything worked. So I didn't have to go into any real troubleshooting.
Yeah.
Just clean the thing up. I've got 75 E4s and KWS1 and that error. And now, I went through get rid of the black beauties, putting in the orange drops and all that. Teflon sleeving on it makes a difference the more you do. So ours, the black beauties are terrible. I mean, the old paper electrolytics.
On the topic of contact cleaning, my approach is to use a piece of clean typing paper with some deoxit on it, and put that in the contact. So most contacts have a coating of silver or gold for good conductivity, but they don't want to put any more than is needed on there, so it's very thin. So if you use anything abrasive, you'll take away the silver, and now you're left with a copper or steel that's going to oxidize very quickly. So you definitely want to avoid anything abrasive, and I just use a little typing paper, and then it'll come out with a little black mark on it, so you're getting the alcohol. The other thing about the oxide,
you've done your job.
yeah, the other thing about the oxide is you don't want to get it on phenolic switch wafers, which is what the alcohol stuff had in it, because it can cause the wafers to swell.
Outside connections, you use a flooded heat shrink. That works pretty well. On coax, mocap. I don't know if you're familiar with a mocap. It's a stretchable rubber that only sticks to itself, so when you peel it off, after years, the connectors are perfectly clean.
Let me take another question.
Yes, hi, I've been very interested. I've got an ICOM Node, ICOM 735. It's got a flaky encoder. You can turn the knob and it may go from 7.1 to 7.2. And if you try to reverse the rotation, you'll still go to 7.3 or something like that. How would you trace the digital signals from the encoder?
A typical encoder like that has two signals coming from the encoder that are 90 degrees out of phase. So one of them is a pulse train going up and down. The other one is a second pulse train where its rising edge is in the middle of the other pulse. By looking at how those pulses come in, they can tell which way to turn the knob. And my best guess is it's a connector. So that encoder is a little device that ICOM buys from a manufacturer and has probably 4 inches of wire and a little connector on the end, and that plugs into a circuit board.
Right.
My bet is it's the connector.
Connector?
It's a connector for that. That's probably what it is, because it's an optical device. If dust and a lot of crud got in it, if you were in a bad environment, that could also explain it. But my best guess on that one is the connector.
I only have a 20 megacycle scope. Can I see those pulses?
Yeah, those pulses are very sensitive.
Oh, very
You'll see a fine with 20 meters. So.
Oh, okay, very good. Thank you.
Any other questions?
The 756 Pro, did they solve those couple of problems?
No, they
went to the Pro
well, they did solve the thumping problem in the Pro. They didn't completely solve the fluty audio on CW in the Pro 2. It was better because I think they changed some signal on it, but it wasn't completely.
I think it did feel really screwed on. I have a Pro 2. I never really listened to it.
So you'll notice it on strong CWs. You have to have the S meter going above S9. And some of the other hints are, if you notice it, and if you can hear it, if you turn on the noise reduction, even if it's turned off quite a bit, it'll go away for a little while, and then it'll gradually come back. And what's happening is the noise reduction is actually reducing the gain through that stage, just down to the point where it doesn't distort anymore. But then the noise reduction adapts and kind of brings the gain back up again. There it comes back.
There's probably no room in there to put in a better low-pass filter.
Well, I experimented with that, and the problem is that the place where you have to put it is inside the DSP unit. The DSP unit is completely enclosed in a shield can that's soldered all the way around to the board. So it's inaccessible.
So they still have that cheap audio ramp IC in there?
Yeah. The 7610 is much better. And I don't know, I never had a 7600. But in that evolution of radios, I think eventually fixed it.
I think I don't know what it was.
All right, thank you everybody for coming to the presentation.